Okay, welcome everyone. So we're very happy today to have Mark Mclean who will tell us about Gromov-Witten invariants for symplectic orbifolds. Please, Mark.
Great. Okay, so yes, I'll be talking about Gromov-Witten invariants for symplectic orbifolds. And this is joint work with Alex Ritter, and it's ongoing. So the aim is to construct Gromov-Witten invariants for symplectic orbifolds. Now, this was done already by Chen and Ruan 20 years ago. But we wanted to define more general counts and sort of set it up in a way which is amenable, which will work for these more general counts. We want to present these moduli spaces, the moduli space of curves, in terms of global Kuranishi charts. I'll explain what those are later. And the real reason that we did this project was because there's a larger project that I'm doing with Alex Ritter, which aims to prove a version of the Crepin resolution conjecture for birational orbifolds. And this was the reason for us writing this paper. Yeah, but so this project is a small part of a much larger project. Okay, so I think but I don't know if I think there's ongoing work by Mac and Sefardini and Ivan Smith, where they just look at the case where the orbifold is a manifold modulo a finite group, so a sort of global quotient orbifold, and they use sort of similar related techniques, but I won't talk about that. Okay, so let me just remind you what how we should think of orbifolds. So they're like manifolds, but they're locally modeled on the Rn modulo a finite group action. So locally they're of the form an open subset of Rn modulo a finite group. The way I will think about orbifolds is as follows. So suppose we have a smooth manifold M and we have a compact Lie group acting on it. And this group action has finite stabilizers, so it acts sort of semi-freely. Then the quotient M mod G is naturally an orbifold. And we can construct these orbifold charts via the slice theorem. So if you have a point in M, and then you can find you can look at the stabilizer group of that point, Gx. So if the point is X, we can look at the stabilizer group Gx, and we can find a submanifold which is Gx equivariant so that we get the following diffeomorphism. So this is a slice. So it's essentially like a submanifold which is transverse to the orbits, essentially. So this is how I will think of orbifolds, essentially as a manifold modulo a compact Lie group. And this slice, you can shrink it so it looks like a coordinate chart. So if I have an orbifold X, which is equal to M modulo G, then there's an underlying coarse moduli space, which is, I'll just think of as a topological space, which I'll write as X underline. And there's a theorem by Pardon which says every smooth, well, let's say closed orbifold. I should have put closed here. Every closed orbifold is a quotient ebb mod G. So we can always think of orbifolds as M mod G. So and if we have two orbifolds, we can think about morphisms between them, and we'll think of a morphism between them. It's fine to think of it in this way, which is you take so we have two orbifolds M1 mod G1 and another orbifold M2 mod G2, and then we have a morphism between these orbifolds. And what we do is we take a principal G1 bundle over M1 and a principal G2 bundle over M1, and we which is G1 equivariant, and we map it equivariantly to M2. So P is a smooth manifold. It admits a G1 cross G2 action, and pi is the map pi from P to M1 is a principal G2 bundle, and the map F is G2 equivariant. And I suppose you should think of it as an equivalence class of such diagrams, or you could, be more fancy, but we'll just, we'll think of it as an equivalence class of such diagrams. That will be fine for us. Locally, this map you can think of as, if you have two orbifold charts, then locally this map is an equivariant map between those charts. Okay, so this is so in particular, if you have a chart V1 gamma 1 and a chart V2 gamma 2, then you get an induced morphism of groups associated to these charts and an equivariant map, a gamma 1 equivariant map. So this is a very sort of quick summary of sort of orbifolds and morphisms between them. But we'll need this later. So I'll just we need this. So here is so a symplectic orbifold is a smooth orbifold X together with a closed non-degenerate 2 form. Or if you think of it as M mod G, then it's an equivariant closed 2 form on M, so that on the slices it's non-degenerate. And in a similar way, we can define compatible almost complex structures on these symplectic orbifolds, and we have the usual theorems like the space of such J's compatible almost complex structures is contractible. So let us fix a symplectic orbifold with a compatible almost complex structure. Let's call it X omega J, and we're going to fix a homology class in the coarse moduli space X bar. Okay, and we're going to look at the moduli space of J holomorphic curves mapping to X, representing beta. But I need to explain what those words mean in more detail, because the curves will also be orbifolds, and there's some special things that we have to pay attention to. Oh yeah, sorry. So similarly, we can define a complex orbifold to be an orbifold with an integral.
Question when you define this symplectic orbifold.
Yes.
Since this orbifold you have a finite group action.
Yes.
And the non-degenerate 2 form should be under the group. Should that be equivalent or? Yes.
So in the charts, so there's a Moser theorem which says something like, which says that locally your symplectic orbifold looks like an open subset of R2n with the standard symplectic form, and the chart looks like that, and with a finite group action by a finite subgroup of the symplectomorphism group. So locally symplectic orbifolds.
I see. So like the finite group action actually is through the symplectic group. Okay.
Yes.
Okay. Yes. Thank you.
Okay. So similarly, we can define complex orbifolds to be orbifolds with integrable, almost complex structures, or you could define it in the same way as you define a smooth orbifold, say with charts, there's several ways of defining it, but we'll define it as an orbifold with an integrable, almost complex structure. Okay, so now we need to know what the domain of a holomorphic curve, the domain of our curves mapping to this symplectic orbifold is. And these are called twisted nodal curves. So twisted nodal curve. So these were defined by Abramovich and Vistoli, I think. So twisted nodal curve. So I'm going to think of it as a space sigma tilde modulo an equivalence relation. Sorry, and this should be sigma tilde, not sigma. Where so sigma tilde is a one-dimensional complex orbifold, and this equivalence relation tilde identifies a finite collection of distinct points. Okay, and so these points that we're identifying, they're the nodes of the curve. So you should think of a twisted nodal curve as a bunch of components, let's say, and they're glued together along points, so they form nodes. And at these nodes, a balancing condition has to hold. Okay, so this balancing condition is as follows. So the balancing condition is at the point P, there's an orbifold chart, and this orbifold chart has some complex coordinate z, because it's a one-dimensional complex orbifold, so there's just one coordinate. And the group action on this chart is the cyclic group of order k, and it just acts by multiplying by on the left by z, by e to the 2 pi m mod k. So the generator does that, 2 pi I m mod k. So this is the group action. And then at Q, there's the opposite group action. So you have a coordinate W, and it acts in the opposite way. And here is a sort of, I don't know if it's a very good picture, but this is a picture of a twisted nodal curve. And I've tried to sort of show glue. It's sort of like this picture is maybe it could look like it has two components, and let's say we glued along the curve along an orbifold point, and the group actions are these cyclic group actions with opposite coordinates. Okay, so that's a twisted nodal curve. And so this balancing condition is important. I'll explain. I think I'll explain in a minute why it's needed. So sigma tilde is called the normalization of the curve sigma, and the points that we've identified together are called the nodes of the curve. Okay, so this is a sort of definition of a twisted nodal curve. So near a node, twisted nodal curve looks like the following variety. So it looks like x times y equals 0, modulo this finite group action. Okay, but the group action is it acts on the coordinate x via g and via g inverse in the opposite direction. So this is sort of like a chart of my twisted nodal curve at a node. And the balancing condition, so the reason why the action has to be of this form is that it allows the node to be smoothed. So the balancing condition, so I can take this equation x times y equals 0, and I can replace it with the equation x times y equals t. And this smooths out the node. And that only this equation I've highlighted only makes sense if the balancing condition holds. So only if my twisted nodal curve has charts at the nodes that look like this. Otherwise, otherwise it doesn't work. So that's a twisted nodal curve. And well, a twisted nodal curve has to have marked points as well. So in Gromov-Witten theory, you're counting curves with marked points, and those marked points map to, say, cycles. So a marking on a twisted nodal curve is a collection of distinct points away from the nodes, and they contain all the points with non-trivial stabilizers except the nodes. So all points on a twisted nodal curve with non-trivial stabilizers have to be marked points. Maybe one other thing to mention is that the twisted nodal curve, it has to, the sigma tilde, its normalization has to be an effective orbifold. So that means the group actions are always faithful. Okay. So that's a twisted nodal curve. Yeah. So a twisted nodal curve with H marked points is a twist. I'll write as sigma P1 to PH. And then a twisted nodal curve mapping to my symplectic orbifold X is a morphism from this twisted nodal curve to X. And the way I'll think about it is, well, it's, if I take the normalization of this curve, then it's a morphism of orbifolds from the normalization of this curve, so that it agrees on the nodal points that I've glued together. So oh yeah, so the first condition is that the induced map of stabilizer groups is injective. So remember, a morphism locally is given by it maps one chart to another chart, and there's a group homomorphism associated to those charts. So map from gamma 1 to gamma 2, and then it's equivariant. And so, yeah, and so at every point we have an induced map of groups like this, and we require that map to be injective. And then the second condition is that the map of underlying coarse moduli spaces is continuous. So what I mean by that is that this morphism agrees when so a twisted nodal curve is its normalization modulo an equivalence relation, and this map has to respect that equivalence relation. So that's what a twisted nodal curve is. I haven't I haven't at the moment, I have not imposed any this doesn't satisfy any PDE or anything. So it's just a smooth, like a C infinity map of orbifolds at the moment. There's no constraints. There's no PDE that it satisfies or any constraints at the moment. So it's just a smooth map, which is injective on stabilizer groups, and it's continuous on the underlying coarse moduli spaces. And I think of the genus of U as the arithmetic genus of the underlying coarse moduli space of the domain. So the underlying coarse moduli space of the domain is actually also a nodal curve, and then you can take its arithmetic genus, and that's what the genus is for me. Another way of thinking about it is if you smooth all the nodes, then you get a smooth curve. If you smooth all the nodes of sigma bar, then you get a smooth curve, and the genus of that curve is what I'm talking about. Okay. So if we have a smooth map from a twisted nodal curve to our symplectic manifold X, then we'll call it stable if it has only finitely many automorphisms. Also, those automorphisms have to preserve the marked points. So it sends the marked point P1 to P1 and P2 to P2, etc. So say, for instance, constant maps could be, you could, you can have constant, say, genus 0 maps if you add enough marked points that are stable. Okay, so I'm going to let MGH beta X be the moduli space of stable J holomorphic maps from genus G twisted nodal curves to X representing B beta. Okay, so this is the moduli space that I'm interested in, and we want to do Gromov-Witten theory with this. So we want to count curves passing through cycles, or equivalently, we want to integrate de Rham forms pulled back via evaluation maps. So in particular, we want to put a fundamental class on this moduli space. Oh, so I have some example. So M could be a point, and then G could be, say, I don't know, any finite group really. And then this moduli space is equivalent to the moduli space of twisted nodal curves together with a Z mod 2 principal bundle over it. And Abramovich, Korty, and Vistoliev written about these kinds of moduli spaces, again, about 20 years, more than 20 years ago. Okay, so we wish to put, as I said, we wish to put a fundamental class on this moduli space so we can define Gromov-Witten invariants. So what I want to explain for the rest of the talk is how we put this fundamental class on this space. And to do that, what we need to do is give this moduli space the structure of something called a global Kuranishi chart. So this is what a global Kuranishi chart is. So it's a quadruple G, T, E, and S. So G is a Lie group acting semi-freely on a manifold T. E is a G vector bundle over T, and S is an equivariant section. Equivalently, you could just think of a global Kuranishi chart as a section of an orbifold. That's all it is, a section of an orbibundle, sorry. So if I take T mod G, that's an orbifold, and E mod G over mapping to T mod G is an orbibundle, and S is just a section. So a global Kuranishi chart is just a section of an orbibundle, essentially. But we'll express it in this way of global quotients like this. So T is called the thickening. So and E is called the obstruction bundle. And we say that such a global Kuranishi chart models our moduli space or any sort of topological orbis space if it's homeomorphic to S inverse of 0 mod G. In fact, we have something stronger. So this is I said this is like a topological space with the Gromov topology, but really it's a sort of topological like Orbi space, and this S inverse of 0 mod G models this this topological Orbi space. So for instance, the stabilizer groups agree here and here, for instance. So what we want to do is construct a global Kuranishi chart modeling our moduli space. Okay, so before I do that, maybe I'll explain how to construct the virtual fundamental class. So suppose we have such a global Kuranishi chart, then we can construct the fundamental class as follows. So what we do is we take the fundamental class of our thickening mod G. So this is the base of our orbibundle, and then we pull back the Tom class via the section of the orbibundle, and we cap it with the fundamental class of the base. Okay, so T mod G is the fundamental class in G equivariant homology, and TH of E is the Tom class of the obstruction bundle in G equivariant cohomology. Okay, so that's what the fundamental class is. So for that to work, you need an orientation for the thickening minus the Lie algebra, the Lie algebra G of the Lie group capital G. And we also need an orientation for E. In fact, you just need an orientation for T minus G plus T minus G minus E. So that's all you need. So these bundles are you can choose your global Kuranishi chart, for instance, so that these bundles are stably admit stable complex structures, and as a result, it's possible to construct a fundamental class in say K theory or Morava K theory or something like this, as well as just ordinary rational cohomology. Maybe I'll say another thing. This fundamental class lives in the thickening, but if you want it to actually live in the homology of the moduli space, then you need to take some sort of limit. But it's fine for the class to just live in the thickening. That's something that's quite often just easier to do that. Okay, so that's enough for us to define Gromov-Witten counts, because we can just pull back cohomology classes from X, and we can integrate them against our moduli space. There are some extra things you need to do in the orbifold setting. So not only do you pull back you really want to pull back orbifold cohomology classes. So you really want to work with you really want to work with orbifold cohomology classes. But I'm not going to talk about that here. So there's there's another story there which I'll leave for the moment. And I want to just explain, how do we construct global Kuranishi charts for the moduli space of curves on our orbifold X? Okay, so instead of doing that, what I'll do is do something easier first. And this will be the case where X is a smooth symplectic manifold. So it's not an orbifold, it's just a normal symplectic manifold. And the genus of our curve is 0. And this was done by myself and Mohammed Abuzaid and Ivan Smith a few years ago. But I should recall this construction first and then explain how to modify it in order to make it work for orbifolds. So let me do that. So now X is a smooth, so X is not an orbifold, it's just a normal symplectic manifold. And I'm looking at the moduli space of genus 0 curves. So yeah, maybe the first thing to say is that what we want to do is construct a thickening of our moduli space. So our moduli space sort of embeds in this thickening mod G. And so the thickening will be a instead of, so the moduli space of curves, it's a moduli space of J holomorphic curves, so representing a class beta. And what we'll do is to construct the thickening is what we want to do is construct a moduli space of curves satisfying a larger family of PDEs. And these PDEs are sort of Cauchy-Riemann equation plus a perturbation term. And in order for that to work, we need to somehow model the domains of our curves. We sort of, so at the moment, the moduli space of curves is sort of like an equivalence class of map. It sort of parameterizes like equivalence classes of maps from the domain to X. And the problem is the domain isn't fixed in any way. It's sort of any genus zero curve. And there are many, there are many genus zero curve, there are many ways of writing down a genus zero curve. And so we want to sort of describe these genus zero curves. We want to put them in a family, and we want to identify the domains of our curves in our moduli space with elements of this family. And the reason why we want to do that is because in order to set up a sort of nice family of PDEs, you need to somehow do, you need to do this really. Otherwise, you can't just work with any sort of abstract domain, any genus zero curve. You need to identify with a family. And this is the family we're going to use. So it's the moduli space of genus zero degree D curves with marked points mapping to projective space. Okay, so degree D curves in CPD. And there's this condition that their image is not contained in a hyperplane. Okay, so this is all of these curves are automorphism free, and this is a smooth quasi-projective variety. And we have the corresponding universal curve. And we'll write C0 for the complement of its nodes. Yeah, this is a smooth quasi-projective variety because this condition here is equivalent to being automorphism free for degree D curves in CPD. Okay, so we're going to let CHD be the universal curve and C0HD the complement of its nodes. And then we're going to do the following thing. So in order to set up our equations, we need to make a choice. So the first thing, so before we do that, we have a vector bundle over C0HD cross X. And this is a vector bundle whose fiber over a point P comma X is the space of anti-holomorphic maps from the tangent space at P of the curve to the tangent space at X of X. Okay, so we have some vector bundle over C cross X. And then we have to make a choice. And this choice is, I'm going to call it a finite dimensional approximation scheme. So it's a sequence of equivariant maps from a representation to smooth, compactly supported sections of our bundle Y. And these maps are compatible. So the representation V mu is contained in V mu plus 1, and the maps restrict. Okay, so and then the union of the images is dense. Okay, so this is called a finite dimensional approximation scheme. So this approximation scheme gives us so this bundle Y is sort of parameterizing perturbation. It is telling us is the sort of space of perturbation terms to our Cauchy-Riemann PDE, and this finite dimensional approximation scheme selects very large finite dimensional subspaces of this perturbation scheme.
Sorry, I kind of got lost in notation.
Yes.
So the naught means you throw away the nodes?
Yes. Yeah, naught means I throw away the nodes. Yes, exactly. Yeah.
Okay.
And then I'm looking at, so away from the nodes, these sections are 0. And then there's non-trivial sections of this bundle of anti-holomorphic maps from the tangent space of the curve to the tangent space of X.
Thanks.
And then I'm going to define a moduli space called the pre-thickened moduli space, which in the genus 0 sense is almost the same as the thickened one, but I'm going to call it the pre-thickened one. And this is a space of triples, U, phi, and E. Okay. So phi is an element of F, curly F. So curly F is what I defined on the previous slide. I called it curly FHD, but now I'll call it curly F. So this is the moduli space of genus 0 degree D curves, whose image is not contained in a hyperplane. Okay.
So what's this? I didn't understand like the moral of the story. What is the FHD doing?
Okay, so at the moment, F is a family of curves. It's just some family of curves. Okay. Later on, every curve in my moduli space will map to this family of curves. But for the moment, I'm just selecting an element from this family of curves. And then I'm mapping the corresponding fiber to X. And then it satisfies this perturbed equation.
So the F is supposed to have all the curves. It's supposed to be some kind of
so
curly family.
F, yeah. So curly F is it's not so yeah. So curly F is this space here. So I don't know if I can highlight things anymore. Oops. 1 second. Oopsie. Oopsie. I think 1 second. That's the wrong slides. Sorry. Do I enlarge this? Uh-oh. I think I pressed the sorry, I'm just going to have to stop sharing and then reshare again. Apologies.
Okay.
Sorry, I think I pressed the wrong button and I got lost. Can I reshare?
Yeah.
Sorry. Share. Doesn't make sense. Wait. Share. Is that sharing the screen? Okay.
Yeah.
Okay. So yeah, so I have CHD and FHD. So FHD is the moduli space of curves of degree D mapping to CPD. Okay, so it's some moduli space of curves in CPD. Degree D curves in CPD.
Degree D in PD, what does that give? Is it
well, it's just some moduli space.
okay.
I mean, it's some nice smooth moduli space. So I'll explain why in a minute, why it's degree D curves in CPD. And I'll give an alternative description of this moduli space in a minute. And then over F, so I'm going to call this F from now on instead of FHD. And over F, I have a curve C. Okay, so that's what this F is here. When I define this pre-thickened moduli space, I have this F here. And this is the moduli space of degree D curves in CPD that are automorphism free. So there's no automorphisms of these curves. So it's some smooth quasi-projective variety. And over F, I have a curve C, the corresponding universal curve C over curly F. And I need a map. This U is a map from this curve, the fiber of this curve at the point phi to X. And then there's the third element, which is E. So I have U, phi, and E is a section of this bundle. So E is an element of V mu, and V mu maps via this finite dimensional approximation scheme to a section of this bundle Y of anti-holomorphic maps from the tangent space of the curve to the tangent space of X. And once you've chosen this triple, then you can write down this equation at the bottom of the slide. And this equation is our perturbed Cauchy-Riemann equation. So d bar Ju is lambda mu of E at the point P U of X. Okay. So the pre-thickened moduli space is, I mean, at the moment, there's nothing really special about F. F could be any family of curves. And you could define this moduli space from any family of curves. And that's all I'm doing, essentially. But in a minute, I need F to be a particular family of curves. Okay. Oh, yeah, you can put a topology on this space. And it's the Hausdorff topology on the graphs of these maps viewed as subsets of C cross X. And that's equivalent to the Gromov topology. There's actually a better topology you could use, but it gives you the same thing. It's I mean there's other descriptions of this topology as well, but this is the simplest one, I think. Okay, so that's the thickening. And well, I called it the pre-thickening because it's not quite right. But we need an obstruction bundle over this. So this pre-thickened moduli space is a family of curves satisfying a family of equations. And we want this parameter E to be 0. So when you set this parameter E to be 0, then you have a genuine holomorphic curve. So inside this pre-thickened moduli space, you have a family of holomorphic curves. So a naive guess for the obstruction bundle would be V mu, because if you set E equals 0, then this pre-thickened, the subset of curves where you set E equals 0 will be the subspace of pre-thick curves in this pre-thickened moduli space, which are holomorphic. And this would be fine if the group G was PGL. But this doesn't work because you can't make this finite dimensional approximation scheme PGL invariant. It's impossible. So this won't work. So we need to somehow reduce the group PGL to PU. So maybe I should say one more thing. So if I go back to the definition of the space curly F, this is the moduli space of genus 0 degree D curves of inside CPD. And one thing that you have on this space is that PGL acts transitively on this space of curves. And the stabilizer groups are exactly the automorphism groups of the domains of these curves. So this is one of the reasons why we choose this space curly F. Okay, so let me go back. Okay, so we need to reduce the group PGL to PU, and to do that, we need additional structure. And the structure we'll choose is we need to choose a Hermitian line bundle on our symplectic manifold X. And we need to choose it so that its curvature form tames J. It's a non-degenerate two form that tames J. Okay. So we can always choose such a Hermitian line bundle. You know, you can just take omega, you can perturb omega very slightly so it still tames J, so that it's rational. And then you scale omega so it's integral. And once it's integral, you can find a Hermitian line bundle whose curvature is that integral two form, and it tames J. So we choose such a Hermitian line bundle. Okay, and then I have a definition called a framed curve. So a framed curve, this is a triple U sigma F. Okay, so sigma is a genus zero curve. U is a map from this genus zero curve to X that represents beta, and F is a basis of H0 of U star L. Okay, and now I've chosen D to be the dimension of H0, 0. And D is going to be the same D that I used earlier when I said F is the moduli space of curves in CPD. So F is called a framing, and the purpose of F is interesting. So this is an idea by Bernd Siebert when he defined Gromov-Witten when he did define Gromov-Witten invariants in the late 90s. So if you have a moduli space of, if you want to, one thing you need to do when you define, say, the virtual fundamental class is you need to stabilize the domain. And the way that, say, Fukaya and Ono would stabilize the domain is they would take the curve and they would choose like tiny little transverse codimension 2 submanifolds to that curve. And where they intersect, that would add marked points to the curve. And you add enough marked points so that the domain becomes stable. And so once you have a stable domain, you can write down an appropriate family of equations to construct your thickening. And that's what Fukaya and Ono do. But the problem with that construction is it's not a global thing. But Bernd Siebert realized you can do something globally. You can stabilize the domain in a global way. And so what you do is you choose a framing. So this framing F stabilizes the domain. So as soon as I've chosen a basis of H0 U star L, this basis stabilizes the domain of the curve in the sense that if I have an automorphism of the curve that lifts to an automorphism of U star L, and that automorphism fixes the basis, then that automorphism must be the identity map. So let me give you an example. So if, let's say, sigma was P1, and then U star L was O1, then, well, O1 has two sections. Oh, was it two sections? Wait, it has three sections forming a basis, and those correspond to the two sections. What am I talking about? They have two sections corresponding to a basis. Those two sections you could choose as to be the homogeneous coordinates of CP1, and there's no automorphism that, every automorphism fixing those homogeneous coordinates will be the identity map on CP1 because they're coordinates. Okay, so that's what a framing does, this F. So if you have a basis of a line bundle and the basis and the line bundle is very ample, which is true in this case, or the line bundle is globally generated, then it induces a map from the curve to CPD. So the map is defined as follows. You choose a trivialization at each point sigma of your line bundle, and then that gives you coordinates, homogeneous coordinates in CPD, tau f0 of sigma up to tau fd of sigma. So if you have a basis of a line bundle and the line bundle is globally generated, then you get this map to CPD. Okay. And so as a result, we have an identification of the domain with this curve with an element with the domain corresponding with a fiber of the map curly C to phi f. So this curly C is CHD, which is what I defined earlier. So a framing identifies the domain of my curve with a domain in this family of curves that I defined earlier. So this family of curves, curly F, can actually be defined in an equivalent way. It can be defined as the moduli space of curves, say genus 0 curves, together with an ample line bundle of an appropriate degree, together with a basis of that line bundle, and up to equivalence, and that moduli space is equivalent to this curly F. Okay, so I have this moduli, I have the space of all framed curves. And what I do is, so the next thing I need to do is I want to, so these framings are, I can change a framing, and that's an element of GLD plus 1, which will change my framing. But really, I want to reduce this group GL to the unitary group, and so I need a vector space telling me how far I am from being unitary, and this is this space curly HD plus 1. It's the space of D plus 1 by D plus 1 Hermitian matrices, and I have an identification. Oh, sorry, this is HD plus 1. So I have an identification of HD plus 1 with PGL mod PU. So this vector space is telling me how far I am from being unitary. Okay, so I have a map. I have a matrix A sub F for any framing F. I have a matrix A sub F, and it's the inverse X inverse of B. And B is the matrix with this IJ entry. So these FIs and FJs are the framing elements. And I pair them up and I integrate them over some volume form, which is the pullback of the symplectic volume form. And this is some matrix, and I measure how far this matrix is from being unitary. Okay. So now I can define the thickening. So the thickening is the space of tuples U sigma Fe. So U sigma F is a framed curve, and E is an element of V mu, which is this vector space of perturbations. So this finite dimensional approximation scheme. And I require that when I identify my domain with an element of F, I require that this element is an element of the pre-thickening. So this is the thickening of the moduli space, and I can and I have a group G, which is the projective unitary group, and it acts on the thickening T via the automorphisms of CPD. Sorry, this is CPD here. This is not PN, CPD. And the obstruction bundle is the space of Hermitian matrices cross V mu, and this has a natural section, sending this quadruple to AFE. So this is the description of the global Kuranishi chart for for my moduli space of genus 0 curves. Yes, so this is the global Kuranishi chart describing my moduli space. Any questions about that? Because there is a lot of notation, and I don't know if many people followed or not. So maybe in summary, maybe I'll say things backwards. So you have you have a curve mapping to X. You use you choose a framing for that curve. That framing identifies in a unique way the domain of that curve with an element of curly F, which is some specific family of domains. And over that specific family of domains, I have a perturbation scheme, and I use that to construct a family of PDEs, which is used to define the thickening. So that's the sort of structure of this construction.
Yeah, excuse me.
Go ahead, Rina.
I have a question. So what kind of space is T? Is it a scheme or is it just a
no,
set?
it's just a manifold.
A smooth manifold.
Yes, a manifold. Well, it's almost a smooth manifold. It's actually a topological manifold with a bit of extra structure.
Oh, okay.
But you can sort of you can change the construction slightly and make it smooth. So you may as well pretend it's smooth. Yeah.
Thank you.
But yeah, so yeah, sorry.
I was going to ask, you had this sequence of what do you call this V, I forget the notation. So you had this family of V.
The perturbation scheme, the finite dimensional approximation
V
scheme,
right? You call them V.
Yeah, let me go back to that. Here it is. Yes. Here it is.
Yeah, right. So what's the role of the family of the sequence?
You know, ideally what you would want is your thickening to be this moduli space of curves satisfying d bar equals any perturbation. So d bar equals anything essentially. So that'd be some infinite dimensional space of curves.
Yeah.
And over that infinite dimensional space, you have I don't know, morally you would have like your section S, which is sort of supposed to be like the d bar operator essentially.
Yeah.
And so, that's how you set up the moduli, this infinite dimensional thing. But what this V does is instead of having any, d bar equals anything, you want d bar equals a particular function. And that particular function essentially lies in this vector space V mu.
Yeah. So my question is, why is there a sequence of V mu's?
Well, because you want it to be arbitrarily close to a general function. So actually these thickenings get thicker and thicker. They get big. They're finite dimensional manifolds. They get bigger and bigger and bigger and bigger. And at each stage they're closer and closer approximation to this infinite dimensional infinite dimensional thing. And the reason why the reason why I choose this sequence initially is because I want to say that so I want to prove that the thickening T is a manifold, and to prove it's a manifold, I need the co-kernel of the linearized PDE to be 0, and that's equivalent to essentially this vector space V mu sort of containing the co-kernel of the d bar operator, and so you want this V mu to be as large as possible. So there's a theorem which says this thickening is a manifold when mu is sufficiently large. So that's why I chose
the entire thing, or do you don't need any local stuff?
Sorry, say that again.
So you're saying that for a mu large enough, this becomes smooth for like the entire moduli space becomes smooth?
Yeah, it contains the entire moduli space. Okay. So that's the advantage of this over, say, Fukaya or whatever, which is a local construction. There are downsides to this construction, which I could say at the end afterwards or something.
Okay.
Yeah. Yeah. Oh, it's time's up.
You can keep going. You can keep going for a little bit.
Maybe I just want to say what we do for Orbif. I just want to say something new.
Yeah, it's okay. If you take 10 more minutes or something, it's fine.
Okay, maybe I'll say this. Maybe I'll sort of rush through it, partly because I just want to mention some results which I think is important for the Orbifold case. So there are two issues that you have to resolve, and one is the fact that twisted nodal curves don't map to CPD because you want the stabilizer groups to inject, and CPD is an orbifold with trivial stabilizer groups. And the second problem is that line bundles on higher genus curves aren't unique. And that this construction actually relied on the fact that there's a unique line bundle of each degree on a genus zero curve. So the second problem has already been dealt with in some later work by myself and Abuzaid and Smith, and also has been dealt with by Mohan Swaminathan and Amanda Hershey as well. Maybe their construction is better, so you should probably read theirs if you're interested in higher genus curve constructions. But I want to deal with the first problem, which is you can't map twisted nodal curves to CPD. So instead, we use a work by Ross Thomas, and we replace CPD with weighted projective space. Okay, so I'm not going to explain what that is because in the interest of time, but it's some orbifold essentially that looks a bit like projective space. So this is the definition. And if I have a complex manifold with only cyclic quotient singularities, then I can use a line bundle to map this orbifold to weighted projective space. And the idea is so we have a line bundle L, and we say it's locally ample if the stabilizer group acts faithfully on the fibers. So orbibundles, the group of the orbifold, the stabilizer groups act on the fibers, and you want them to act faithfully. And we call it globally positive if some power of this line bundle is a pullback of an ample line bundle from the underlying coarse moduli space, which is a variety. So we say it's orbi ample if it's locally ample and globally positive. So this definition really only makes sense in the case when you have cyclic singularity, cyclic stabilizer groups. But that's the case for twisted nodal curves. The stabilizer groups are Z mod KZ. And then using this, we can choose a basis of the powers of the line bundle to embed our complex manifold into the weighted projective space. So we choose something called a K-framing, and it's a basis Fij of powers of the line bundle. So I choose powers of the line bundle, L to the K up to L to the 2K, and I choose a basis for H0 of each of these bundles, each of these powers of these line bundles. Okay, and then I define a weighted projective space, and it has these weights. There are N1 copies of K, N2 copies of K plus 1, and NK copies of 2K. So there's some weighted projective space with a bunch of Ks, weighted by a bunch of Ks or K plus 1s, etc. And using this basis, I can map my complex manifold to this weighted projective space. And if K is sufficiently large, this map embeds this manifold into weighted projective space. So maybe I'll just sort of finish my talk by saying what we do is we use this result by Ross Thomas to map the domain of our curve into weighted projective space. And we look at the moduli space of appropriate curves in weighted projective space and use that to build our global Kuranishi chart. There's a copy of these notes, I think, in the chat, or Lino can post it again, and it has all the details. But I don't have time to explain all the details. But I just wanted to mention this result by Ross and Thomas. And that's the sort of main tool that we use to pass to go from manifolds to orbifolds. So I think I'll stop there.
Okay, thank you very much. Questions? So it's your chance, because then I'll start asking questions and it might take a while. Okay, so I wanted to ask again about this. So in the usual thing, right? So you have this D bar, right? It's a Fredholm
Yes.
operator. So you know there's this finite dimensional thing.
Yes.
That covers the co-kernel, right?
Yes.
And so here you're trying to do this kind of a global way, right? All at once.
Yes. Yes.
And so then is this some sort of like compactness argument that like if you go big enough, you cover the entire moduli space?
Well, it's all I'm using is the fact that the moduli space is compact. So if this V mu is large enough, for any given holomorphic curve, I can choose V mu large enough so that it contains the co-kernel.
Yeah.
So it maps surjectively to the co-kernel. But then by compactness, but then for nearby curves, it also surjects to the co-kernel.
Yeah,
and so by compactness, for mu large enough, it surjects for every holomorphic curve. So that implies that this thickening is a manifold containing essentially our moduli space. But the cost is you have to choose a framing for each curve. The framing identifies the domain with a.
Yeah. And what happens near the nodal curves?
Well, I mean, it's just
do you like, are your things like, so in Fukaya's approach, right? The things are honestly holomorphic.
Yes, honestly holomorphic near the nodes, because these finite dimensional approximation scheme is sections of the bundle which are zero near the nodes. That's why I use this C0.
Okay. And so then you're saying this gives you a topological manifold and not
well, it gives you a manifold with something we call it a C1 lock structure. So the fibers have it's a manifold and it has a map to this curly F. And the fibers have a smooth structures and the base has a smooth structure, and they're somehow compatible. And this is called a C1 lock structure. But you can.
So is it the usual problem of like coordinates near the nodes being kind of weird?
Yeah, basically yes. So that's the best you can do with gluing. And but then there's this result by so what you can do is there's a result by Lashoff from the 70s, and that essentially says if you have something like this C1 lock structure, then up to stabilizing, so up to crossing your manifold with a representation, a G representation, you can find a G equivariant smooth structure. That's sort of and it's unique. It's unique up to contractible choices. So you can sort of enlarge your thickening in such a way that you get a smooth structure on it, and you can make all the evaluation maps smooth submersions and everything. But that's a topological result from the 70s about G equivariant manifolds admitting. It's a result which says if you have a G equivariant topological manifold and this G action lifts to the microbundle, there's something called the tangent microbundle, and it lifts equivariantly to a vector bundle, then it admits a smooth structure up to stabilization. And so you can use this result of Lashoff to put smooth structures on the moduli spaces, which is again, it's handy when you want to talk about something like K-theory or something like that. So yeah, it's not essential, but it's very handy.
Okay, and you can do this and you can do K-theory with this?
Yes, yeah.
Okay.
So in the non-orbifold case, this was explained. This is done in a paper of myself and Abuzaid and Ivan Smith. We explain how to do K-theoretic Gromov-Witten invariants for all genus in the smooth, the non-orbifold case. And it works in the same way for the orbifold case essentially.
Okay. Also in the orbifold case.
Yeah. So I mean, essentially, once you have global Kuranishi charts, from that data, you can construct your K-theoretic virtual fundamental class.
Okay.
So yeah, again, you can you work there you work with K theory of you have this group G acting on the thickening T, and you look at K theory corresponding to G equivariant bundles on T, and you build a fundamental class on that on that in that context. Yeah, I don't know if I can say more about that.
That's okay.
Yeah, but you need like a spin structure to construct a fundamental class. So a sort of appropriate spin structure on tangent space of T minus G to put this fundamental class on there.
Okay, thank you. So let's see if there are more questions before we let you go. Okay, there's less chance. If not, I think we'll stop here. Thanks a lot.
Okay, yeah, no problem. Great. Thank you.
Bye-bye.
Okay, bye-bye.